My name is Jeanette Mumford. I'm at the University of Wisconsin-Madison, and I work at the Center for Healthy Minds. And my background is in biostatistics. That's what I got my PhD in. But for fMRI. So fMRI is my focus. So today what I'm going to talk about is kind of the differences between machine learning and statistics, as well as the similarities. And machine learning can be thought of as being the two fields of computer science and statistics joining in a sense to create this machine learning thing. And sure enough, you'll find people who practice machine learning in computer science departments as well as in statistics and biostatistics department. And yeah. So the things I'm going to focus on are if machine learning is the same as statistics, and if not, what is machine learning telling us that statistics aren't, and vice versa. I'm also going to talk about whether or not machine learning is better than statistics. And then the things that keep me up at night, things to consider when you're transitioning from traditional voxel-wise statistical analyses to machine learning. So keep in mind, I typically work with functional data, so that tends to be how I think, but I think this would also apply to structural voxel-wise data or resting state data across the board. So let's start with the machine learning versus statistics. So here's a really simplified comparison. So statistics really focuses on inference and mechanism. So when you run a statistical model, so think of linear regression, and I'll have an example with that, you're focusing on telling a story typically. Like these things are related to this thing. And we believe that's the case because of theory, and these things are statistically significant and these other things aren't, and that goes with our theory. So that's typically what you end up doing with statistics is you're telling a story about mechanism. Machine learning, on the other hand, is more interested in, and this is just broadly speaking, this isn't necessarily always the case, but the goal of machine learning is prediction. So you kind of put the mechanism part aside. So if you think of Netflix giving you recommendations, all they care about is they dump in everybody else's ratings of things and information about you, and that they get an accurate prediction for what you would like to watch. They don't really care what's driving it, right? They just want to dump a bunch of data in and get a good prediction out of it. So generally, that's broadly where machine learning is coming from. So I have an example which does involve cats, which is makes Loki's appearance quite appropriate. So let's say I'm running a study or I'm collecting data, and the way the study works is, first of all, I'm always going to carry my phone around with me, and then each cat has a sensor on it. And so throughout the day, my phone will buzz, and I have to report how happy I am. And as soon as I enter that report, the phone measures the distance between myself and each of my 3 cats. So I have 4 measures altogether, my happiness at each time point, as well as my proximity to each of the 3 cats. So let's step back and think about what questions we would ask if we were taking a statistical approach. Oh, but first, so here's what the data would look like. So let's say I wake up in the morning and Loki's next to me, annoying me for food. That makes me unhappy. I get away, I'm a little happier. Then he gets closer, I'm like, ugh, you're annoying, less happy. Move closer to the other cats, my happiness goes up. I don't know if you can hear him meowing, but now he's meowing. But that's the basic idea behind this data set. So the statistical approach to this would be to think about, oh, well, I wonder how each cat relates to my happiness and which cats have a statistically significant relationship with my happiness. Data and put it into a linear regression. So this is happiness as a function of the proximity to each of the 3 cats. And then here's the model output down here. If you're not familiar with R, it's fine. These are the parameter estimates here, the standard errors, the t-statistics, and the p-values for each of the cats in the intercept. So the intercept just basically gives the baseline, how happy I am if all 3 cats are near me, because the variable here is distance. So if distance is 0, all the cats are near me. And then What this is showing here is that when the black cat gets further away from me, my happiness goes down. So as distance increases, my happiness decreases, and that's statistically significant. So it seems like I really like that black cat, right? And then this purple cat, a negative relationship as well, but it's not statistically significant. And then we have the orange cat, where the further away it gets from me, the happier I get, and that is statistically significant. So now you can kind of tell the story using statistics that we kind of saw in the cartoon example of me moving around the house. The orange cat tends to make me less happy, the black cat makes me more happy, and the purple cat's kind of neutral, controlling for the other cats. So machine learning, on the other hand, it's a completely different question. The question for machine learning is about prediction. And if I even state the question, it sounds ridiculous. Can we predict my happiness only knowing how close my cats are to me? I hope not. I hope my life has more in it than just that. But the way machine learning works is I'm going to take the betas from this data set. So I'm going to take these betas and see if they generalize to a new data set. So this is just one part of a twofold cross-validation. I know you may have seen Tal's talk prior to this, where he did go through a machine learning tutorial. I'm sure he talked about cross-validation. I had a meeting, so I missed it. But so this is just one part of that. So I collect a second data set. Let's say a week later, I repeat the study. And now I have new happiness measures for each of the three cats, or my happiness measures and new distance measures for each of the three cats. So I'm going to plug in the distance values for the cats, multiply it by the betas from the old data, and compare the predicted happiness values with the true happiness values. So that gives me this plot here. So this is my predicted happiness, plugging in the betas from the first data set, but the distance measures from the second data set to predict current happiness in the second data set. And this is the actual happiness on the y-axis. So you can say there's somewhat of a relationship. I'll talk about it later. Oftentimes people just use a correlation to compare these. That's not a great approach, but you'll see that really common measures are mean absolute error and root mean square error. So mean absolute error, that's just taking the predicted happiness, say here it's about 5, subtracting the actual happiness, taking the absolute value, and then averaging. Root mean squared error is the same idea, except you square the difference, average, and then take the square root. So either way, with either of these approaches, we can see that it's off pretty far, close by 2, so it's not really a good predictor of my happiness. And it depends on the measure you're using, how close you want this to be. So, right, so now a deeper comparison. Before I had a pretty simplistic comparison of these two. And this comes from a video on YouTube, Brian Kaplan's Machine Learning versus Statistics video, which is good. Recommend checking it out. And he talks about these two things. And with machine learning techniques, you'll find they're very user-friendly. You can pick it up very quickly. And since you don't really have to worry about, I'm sure you've heard the word features by now. Features are really the same as regressors. You don't really have to worry about picking them or anything like that. Anyway, you can just dump your data in and see what comes out. The goal, as I said before, is to get good predictions out of the model. It's pretty automated. Other than sometimes there's a parameter selection that you have to do. It's a otherwise pretty automated process. It's a bit of a black box. By that, I don't mean that you should avoid learning what your classifier is doing. You surely should, so it shouldn't be a black box in that sense, but it is a black box in the sense that you don't really get at the, what's the word I'm looking for? The explanation of what things are driving it. You kind of don't care. There's a huge overfitting worry, which we'll see, because you'll get very poor predictions if your model is overfitting the data. And there's this idea of generalizability, which here is the generalizability of, as I was showing in the cat example, the betas to different data. And of course, you need lots of data for machine learning. So if you only have 40 subjects with fMRI data and you're trying to do some type of a prediction, you're asking a lot of your machine learning approach, unless you're doing some sort of data reduction. On the other hand, statistical modeling, you're interested in parsimony, meaning you want to kind of break it down to the things, that the mechanism, finding the underlying mechanism, and which goes hand in hand with the interpretability of the model. And knowledge creation, meaning you've formed some sort of hypothesis based on theory, and it's linking statistical model results with your theory. And of course, this hinges strongly upon inference. The population that you're studying is also important. Generalizability is important. It's in a slightly different context since it's the generalizability of the model and not the parameter estimates. And obviously we can run statistical models with a lot less data than we can for machine learning. So although there's this tendency to talk about these things as being two separate things, there actually is a lot of overlap between the two. And as things are progressing, and what we actually need in our fields, what will help us, I should say, in our field, is to incorporate some of these ideas of interpretability from traditional statistical models into machine learning, and also the idea of inference. And when I say that, I mean taking into account the uncertainty of the data when interpreting results or making choices in machine learning. And so we'll see that even though these two fields are often talked about as being very different, we have a lot to gain from kind of looking at the overlap between them, or how we could include things that are missing from one and the other. So another way of saying that is looking at what we have here in machine learning currently, and then looking at the statistics tube and saying, hey, well, what did we miss out on? And that could be like this idea of inference. But on the flip side, statistics could learn a bit from machine learning and have improvements. So, so this is a slightly different comparison. Before I was talking more about like the interpretation of the models and the way you're viewing the data, but also the fields are very different. And I'm only mentioning this because if you're choosing to study machine learning more, you're going to have to make a choice of who to work with. So do you go to a computer science department or a statistics department? And these are traditionally things that differ between the two, but obviously there are exceptions. So these are huge generalizations. But for sure, machine learning papers are driven by conferences. So you have this fast pace because everybody's publishing papers together on the same schedule. So it creates a synergy in the field as well. So at the end of a PhD where you're following this machine learning track, you'll have a lot more papers than a more traditional statistics type track, or just a vanilla like psychology track or neuroscience. And machine learning has taken some statistics topics that statisticians are like, good enough for us, and the machine learning community is like, oh, but it's not good enough for us. And they've really improved on these methods. And now it can be helpful for the statistics community to adopt those ideas. Also, statistics, as I was saying before, there's some topics there that could be incorporated into machine learning for improvement, and that's this worry about uncertainty. And I have just one example about that really quickly. It's kind of cool, the semi-supervised inference. So if you look at these two sets of data, you might say, oh, okay, I bet the boundary's right here. So let's say that it's really expensive to get these labels on the data. So they could be medical images that you have to have an expert radiologist or somebody look at to give the classifications. So maybe you only have a very small amount of labeled data, but you have tons of unlabeled data. So when I've added the unlabeled data, you might now be creating a very different boundary that's S-shaped. So that's this idea of semi-supervised inference, is can you use the unlabeled data to help determine that boundary? And the statistical concept that they incorporated into this is the idea of the variability. So they use inferential type strategies to determine whether or not you should be using the unlabeled data to create the boundary, or if you should just stick with the labeled data. So that's just one of those examples. So, right, so just to round up this section, the questions and methods that can be answered are generally pretty different between machine learning and statistics. But I think we're going to be able to get at mechanism a little bit more with machine learning with some of the new strategies that are coming out. And if you're considering the differences in the two fields, if you're making career path choices, looking for people to work with, that can be helpful to know. So there was one question. So somebody asked, is there a way to assess the generalization of betas using statistics? Or does it only give us information specific to the data we're working with? Right, you really need an independent data set to see how the betas perform with another data set. With one data set, unless you're doing cross-validation, but that would then be machine learning. But yeah, you would definitely need some sort of cross-validation or something to evaluate that. The bootstrap, you're still only using, so the question is with the bootstrap account, that's just really a different way to estimate the standard error for the betas. And I don't think that doesn't really give you a sense of an out of sample because you're still using the same sample to establish that. So yeah, I don't think so. Are there other questions? So you have to use a technique similar to train and test data set as done in machine learning. Yep. If you want to know if it generalizes to an independent data set, you need to have an independent data set, so a training and test set to fully evaluate it. Are there any other questions before I move on? Okay. Okay, so is machine learning better? So one thing I like about machine learning, so it's a bit of a peeve of mine, the overuse of the word predicts. And so someone will run a linear regression, they'll find depressions associated with some brain measure and say depression predicts brain activation. Not really. I mean, you really can't tell that. An association doesn't mean that the model's actually predicted. So in a sense, using machine learning to see if you truly can predict the brain activation or flip it around, use the brain activation to predict level of depression, kind of putting your money where your mouth is. Can you actually predict it? And my feeling is that in a lot of cases, it's like my cat example, right? I had some really significant cats there, right? Two of the cats were significantly associated, their proximity was significantly associated with my happiness. But in terms of predicting my happiness, it's highly unlikely that something as simplistic as taking proximity of cats would be a great prediction. Hopefully other things that are happening in my life are necessary, and they're probably interacting in a really weird way to impact my happiness. So I like the idea of machine learning because it helps us get closer to understanding the true usefulness of the theory in terms of prediction. They're both useful, for sure. Also, a benefit of machine learning based approaches has to do with what's called the bias-variance trade-off. So think of each of these X's as a parameter estimate from a bunch of different data sets in a model. And we want to get that parameter estimate right. But various things can prevent us from estimating it well, noise in the data or collinearities in the model. So let's say we have a bunch of regressors in the model, and maybe we're just focusing on one of the betas in that model. Okay, so the goal is to hit the bullseye. In this first case, we have low bias, low variance. Low bias because we hit the bullseye on average. Low variance because all the estimates across our multiple data sets of this specific parameter are the same. Down here, this is still the low bias case, but it's the high variance case because those estimates are spread out around the bullseye, but on average, we'll hit the bullseye. So what's interesting is in the linear regression world, if that's the world you've been living in, I'm sure you've heard over and over again that the estimates we get from linear regression are unbiased, which sounds great, and it is great. And they have the minimum variance among all unbiased estimators. So that doesn't mean they have the minimum variance overall, just within the category of unbiased estimators. So what we realize is sometimes if we add a little bit of bias, and typically that bias is to take some of the betas and shrink them towards 0, there can be an overall reduction in variance. So this might sound really awful when I'm explaining it because we're so ingrained. The first time I heard it, I was like, I don't want bias, but it actually does make sense. So anyway, and I'll show an example in a second. So here, this is just to finish going through these different combinations. This is high bias, low variance. So the estimates are biased. They're not hitting the bullseye. And here we have the worst case scenario. We never want to be here because we're not hitting the right answer on average and the variance is through the roof. So, right. So why would adding a little bit of bias help? So think of a really simple model where you have two regressors that are doing exactly the same. They're explaining exactly the same thing. They're correlated at 0.95, and you put these two regressors in the model. If you've ever done this, you'll find out that what happens is you get really crazy parameter estimates. The parameter estimate for this one's going to be really huge, and the parameter estimate for this one's going to balance it out by being really small. What's interesting is the overall fit is fine, but the parameters are all over the place. So what you can do, and so if you focus on the estimate from one of those parameters, it's going to be crazy. But if you take one of the parameters and shrink it towards 0, it stops the other one from bouncing around all over the place. I'll show you an example of that too. Oops, sorry. Just really quick. So regression focuses on the sum of squared errors. So just reducing the squared difference between the center and the estimates, whereas the bias variance decomposition allows us to focus on the bias and the variance separately. And we'll see that separating it into those two components and tweaking the bias a little bit and then looking at the improvement in variance can give us better predictions. So this example will clarify that. So the green line here is the true underlying model. And then we have a set of data points shown in blue, which are generated by just simply adding noise to the true model or true actual function, underlying function. So then what is done is a polynomial of degree 15, and I mean, there are hardly more than 15 data points. So when the number of regressors is almost equal to the number of data points, you're going to have overfitting, where the model tries to go through almost every single data point. So that's the variance. So there's no bias. We're not restricting any of the 15 betas. They're all allowed to do whatever they want. And then what we get in return is a highly variable estimate, which you can see here. It's really wiggly. So if I was to use this red line to try to predict values, if I was given the X values, and then I plug them into the function that gives me this red line to predict the Y values for a new data set, it's probably not going to work very well because of the overfitting. So here they used a method called ridge regression. So the way ridge regression works is it differentially shrinks some of the parameters toward 0. And it kind of focuses on the ones that are causing this instability in the model. So one way to think of that is if you have two regressors, as I said before, that are doing the same thing, it kind of diminishes the ability of one of those two to contribute, so the other one can take over, and then that one's estimate is stabilized. So it's the same model except with this regularization from the ridge regression. And you can see we get a much smoother result. It's less variable. So that's the bias variance trade-off. We bias some of the parameters to be shrink them towards 0 a little bit, and we're rewarded with a less variable fit. So this is going to be a better predictor than this model on the left. So hopefully that makes sense, the bias variance trade-off. So you can actually decompose the total error into two components, the variance component and the bias component, and then they sum up, which is what I was showing in the illustration earlier. And as I said earlier, in the linear regression world, so when we're doing explanatory models, it focuses specifically on when we have unbiased estimates, but typically the variance will also be high. So even if it's taking the minimum variance among unbiased estimates, we're here. So you can see the total error is quite high, meaning it's not going to predict very well. Where when we use things like regularized regression and machine learning type strategies, we end up here where the bias is maybe a little bit elevated, but we have the huge benefit of the decrease in the variance, so that total error is much less. Let's see if there were questions. Let's see, cross-validation is sometimes used in statistics without necessarily being machine learning. So the goal isn't prediction? I guess I don't know if you can expand upon that a little bit. Not sure I fully understand. So Amelia, if you can add to that. Oh, and Manjari's here. She can correct me on things. So let's see. Check out CES carrot packages. How you can cross-validate with your regression model and assess generalizability. I think this is the case where the lines between solutions get a little bit blurry. Personally, I think it's a bit arbitrary to say bootstrapping or cross-validation is exclusively statistic or exclusively. Yeah, I don't think. I guess I need an example of cross-validation not being machine learning. I guess I would need to know what the goal of that would be. All right, just working. I don't know if you can see the questions I'm reading, so I should probably be reading these out loud. But training and test sets cannot use a correlation coefficient. Unsure if this answers your question, but I'm unsure of the purpose of using the correlation coefficient when you do a train test assessment. I'll clarify that later. When you use some of the measures shown earlier, you're essentially get an idea of how many times your prediction is correct or incorrect, and for the number of prediction cases, how far off your prediction is. I think that information is more useful to evaluate model performance than a correlation between your predictions and the true value. Ah, okay, now I understand the question and the answer, right. So you can have a perfect correlation, and I'll show an example later. You can have a perfect correlation, but your predictions are always just 3 times the actual value. That's not a great prediction, right? But the correlation would be perfect. Right. Would Lasso do something similar to ridge regression, but with much more stringent measures? So Lasso is different, and that's the way, I wish I could remember how it works because there's a square versus a circle. So the way Lasso regularizes is quite different because it hits a point and then it just sets the beta to 0, whereas ridge regression just keeps shrinking the betas. So Lasso can almost be thought of as a model selection type idea because it's basically eliminating some of your features, whereas ridge regression is not eliminating any necessarily, it's just shrinking their contribution. So yeah, so the regularization is different. And there's a great illustration, I'm not gonna be able to explain it now, in the, not even gonna try, but with the square and the circle. I'll post it later on Slack, but it helps explain why they're so different. It's from the Tibshirani, of course, the first name I think of is like the last author on the book, Hasty textbook, which is a good book. Okay, so hopefully I answered all the questions or you answered them for each other. Yeah, I'm still interested. I don't see how I feel like if you're doing cross-validation, you're inherently trying to do prediction, which to me is more of a machine learning based idea than a statistics idea. But I don't know, it kind of, in a sense, does it matter to put a label on what you're doing as long as you're applying a method that answers a question and you're applying it correctly? Then who cares which bin it falls into or if it's crossed between the bins. Okay. All right. So another motivation, so again, this is the section, is machine learning better. So hopefully you've seen this paper. It's basically establishing probably what a lot of us already know if you've run some voxel-wise fMRI analyses or ROI-based analyses. They're not really reliable when you're looking at individual differences. So it's specific. They're more reliable for group differences or just looking for group averages. But yeah, so this paper delves into that. And so here's the first figure in the paper, which I think is really compelling. So what they have here, so again, just to set up the type of analysis we're doing, the idea is we have some between subject variable that we've measured. I'll use depression again, and we want to know if depression is associated with brain activation differences for some task that our subjects did. So here, the regressor in the model they're referring to is phenotype. So that's what they're talking about here. And ICC is just how consistent this measure would be if you were to take it over and over and over again. So if you were to measure depression multiple times on the same subject, how consistent are their scores? That example almost doesn't make sense because that's something that would fluctuate naturally. Right. The x-axis here is the interclass correlation coefficient of the brain activation estimate. So that's really the more problematic thing here, is that interclass correlation tends to be low. And what I'm going to show you here in their plot is the sample size needed for 80% power to detect true effect sizes of correlations of 0.1, 0.15, 0.2, 0.25, and 0.3. And then these gray colors here just correspond to, they're going to put bands to help us understand what the ICC range we're in, because they have these labels like poor, fair, good, excellent. So this is really discouraging. So most of the ICCs, I'm going to leave out the meta-analysis and the other analysis they did. So for the tasks for which they could include on the meta-analysis, and for the tasks that they looked at from the HCP and some other study that they did that had, where each subject did it twice so that it could calculate the ICC, more or less, things fell between poor and fair. So what this graph is telling me is if the ICC of my phenotype is 0.6, if my true Pearson correlation is 0.1, I don't even have a chance of detecting it. If the true Pearson correlation is 0.3, I'll have 80% to detect that with 350 subjects, where the median fMRI sample size is down here below 50. So ouch, even with 100 subjects, it's not going to help much. The other panels are just increasing the ICC of the phenotype or the regressor in the model. And we can even see here in the best case scenario where the ICC is 1. Again, going to the range where ICCs tend to be for fMRI-based measures, voxel-wise or ROI averages, we still need upwards of 200 to 250 subjects to have 80% power for that pretty big correlation of 0.3. And that's true. I'm not exaggerating. 0.3 is a rather large brain other measure correlation to expect to see in data. So those Cohen's cutoffs for small, medium, and large effects 100% don't apply to neuroimaging. I don't know what they apply to. Every field is different. Effect sizes, signal to noise ratio, that's different. So it's really bad in the case of fMRI data. So that's where we're at. So there are two arguments. One is that we could design better studies that are designed to really increase the ICC. So you need a much stronger response or something. And one argument is a lot of the designs we're using now are specifically designed to lower between subject variance, and you would need to actually increase it in order for this to work. So that's one argument. I don't know what those would be, but the other argument is perhaps you noticed right after this came out, a lot of preprints went up, or maybe two at least that I know of. So one of them, somebody here, maybe not here, but somebody at the course actually mentioned on Slack. And then I just noticed that this is somebody who took, well, I think back under the different name, but they took this course a couple years ago when I taught. So anyway, they're like, whoa, all this talk about how unreliable fMRI is, we can get reliable signals. But that's because they're not using voxel-wise or ROI-based measures. They're using sort of multivariate measures in classifiers or classification type-based analyses. So that is why I am thinking that machine learning type strategies are probably better to, if you're really interested in things like individual differences. I really feel like it's kind of insanity to keep running these voxel-wise analyses looking for correlations with variables unless you've designed this amazing new task that has really great between subject variability and can have higher, stronger effects. So I'm going to check the questions. Okay, so to explain regularization, I have another example. Don't worry, it involves cats. To show basically how the lasso behaves in a minute. So hopefully that'll help with the regularization. And so that's for the question about explaining what regularization means, either conceptually or mathematically. And it helps the overfitting by reducing variability. So let's see, theoretically, when you use more features, you can get a better fit of the data. So think back to when, oh, I see you're explaining the point. Think back to when Jeanette showed the figure with 15 features, really fit the data super well, but it was variable. But it's more complex and not parsimonious. So the regularization is a way to penalize an algorithm for having too many parameters. And so it creates a simpler model. Yeah, that's a way to think about it. Oh, this is great. I don't even have to answer the questions. You guys are doing it for me. Maybe I don't even need to give a lecture. I'm just kidding. To add to Catherine's answer, in your regression equation, when you're fitting your beta values, there's a penalty term that's also being minimized that involves those beta coefficients as well. The different option for the penalty term will make something lasso or ridge. Yep. Different penalties. Regularization is somewhat vague in that it describes a class of models that work rather differently, but that the two that were discussed, lasso and ridge, are introducing a penalty that scales with the number of features. Lasso scales with the L1 norm, ridge scales with the L2 norm, and elastic neck balances the two with some ratio. Okay. The excerpt of the ESL book that Ariel also posted in Slack channel explains with more math. Sounds good. Okay. I think all questions have been hopefully addressed. Okay, last but not least, things to consider if you're coming from a voxel-wise type analysis world and transitioning to machine learning. First of all, go for it, have fun, but I often have some worries. And it's not like I'm literally not able to sleep at night because I'm worried about it, but there are just some common things that come up when I'm working with people who are learning how to apply machine learning strategies. So this is probably the most common one. We're used to having voxel-wise maps. And depending on the strategy that you're using for your classifier, you're not necessarily going to get a very useful voxel-wise map. You can always force the algorithm to give you one, but whether it's interpretable or useful is a whole other question. So this is a map I was sent when someone I was working with, and again, fully supportive, dive in, start analyzing your data, figure it out, make mistakes, find your mistakes, ask questions. That's how you learn. So they sent me this map from their support vector based classifier. And they're like, yeah, why are the red voxels right next to blue voxels? That doesn't make sense. And I also believe there was a region they thought would be here that wasn't here. So it really depends. You have to back up and remember the goal of the classifier. It just wants to find what works. If there's two things that work, it's just going to grab one of them because it doesn't need the other one, because it's going to hopefully lean towards using the more useful features. And I'll show that example in a second. So the weights that you get at the end aren't necessarily reflective upon what is actually, it's basically like the necessary and sufficient. It's sufficient to do a good classification, but it might not be necessary. If you got rid of that, maybe another part of the brain that was highly correlated with the brain could take over and do just as good of a job. So the goal of the classifier is simply to classify, and depending on the classifier you're using, whether or not the feature weights are informative as to relating to your underlying mechanism hypotheses is up for question. So, and it depends on the classifier. So there's some newer approaches. So if you use something like PCA lasso, I feel like you get something slightly more interpretable there, because the first step is to do a principal component, a PCA of the data. And when you do that, you end up with principal components that are independent from each other. And then you apply the regularization to that. So you're not going to run into cases where you had two features that were highly correlated and it randomly selected one because they aren't correlated. So I feel like those results are slightly more interpretable. I know you can take the magnitude of the feature weights from the SVM, and sure, that indicates that those are necessary to give a good prediction, but it doesn't mean that they're the only voxels that could have done that. Yeah, and then there are other approaches I've seen where the features are clustered in some sort of way based on theory, like these voxels should go together, these should go together, these should go together, and then those resulting clusters are really what are of interest. And if those aren't highly correlated, you're not going to have these issues. So here's an example with lasso regression, my last cat example. So let's say my two cats, same study, they're always right next to each other. So they're siblings. So they're like two peas in a pod. They're always hanging out together. So their distance for me is going to be highly correlated. So let's say it's correlated at 0.95. And let's say each cat makes me equally happy. Their true regression parameter is -0.1. So for every 10 feet of increase in distance, my happiness drops by 1 because they're not near me. So what I'm going to show you is I'm going to simulate a bunch of data sets, and I'm going to show you the lasso parameter estimates from each one. So again, just think of it as a linear regression with this regularization. So it's going to shrink the betas. In some cases, it just shrinks them a little bit towards 0, but in a lot of cases, you'll see only one cat ends up contributing. So 0 is here. The blue line is the sister cat. The pink line is the brother cat. The x-axis is the simulation values or simulation number. So this is the first simulation. You can see that the brother cat has a negative parameter estimate, which is actually somewhat close to the truth. And then the sister also has a negative estimate, but it's up here. Remember, the truth is 0.1. And you'll notice it almost looks like, and it's not that it almost looks like this is exactly what's happening. If I actually sum these two parameter estimates, I'll get the right value or close to the right value. Okay, so this is a high collinear case. So you can see that a lot of the times the brother cat's parameter is set to 0. It is for sure not the case that the sister cat in this setting right here, that the sister was better or anything like that. Overall, they are both equally good at predicting my happiness. It's just simply lasso chose one. And you can see there are also cases where the sister's parameter was set to 0 and the brother's was not. And again, the sum of these two will always be closer to the truth, which is 0.1, than typically either one. We can see here, this is a weird result, but this is typical when there isn't good regularization, so I'm not sure what happened here, but you can see we have a wildly negative parameter estimate for the brother and then a wildly positive estimate for the sister. So I would say here the regularization kind of failed, but I don't know, the prediction probably maybe was still good, but So hopefully it gives you the idea, I think, for answering. Now I have to look at the question, what the question was. Now I can't find the question. But about the behavior of the regularization, I think it was pertaining to that. Okay, downside, and other thing I worry about is you actually need more data. So if somebody comes to me and they're like, I have 40 subjects, I'm gonna run a classifier on it, you're really asking a lot of your data. So big data doesn't just mean the data are wide. They do tend to be wider, so we do tend to try to dump all the voxels in as features, but you need to have longer data sets too. They need to be bigger in both dimensions, and you still want to have a ton of data. So that's not great news for neuroimaging, but because the data are expensive. But this shows how having more data can help with the overfitting problem. So even if you have regularization, it can only do so much. But adding subjects can really, really help with the overfitting. So we can see here the true function is in red, the fitted model is in blue. And you can see with just 20 subjects, we have a lot of wiggle and we're not going to get good predictions. But with 200, we have less of an overfitting problem and our prediction will be much better. This is just relating to not using correlation, but to use other measures and to look at the data very carefully. So this is a problem that's been since fixed. At least I know that, I hate when I only remember the last author and not the first author, but Steve Smith is definitely on this paper as well as somebody else. But a common problem in predicting age from structural data can be seen here. So let me just explain here real quick. What we have here on the x-axis is age of subjects. So these are healthy subjects. And then we have what they call brain age. So basically they took a bunch of structural measures and they used those measures to predict the subject's age. So here they're comparing the predicted age to the actual age. And the correlation is nice and high, which is great. But as I said earlier, it's not the perfect way to look at the data or the only way you should look at the data. And in this paper, they for sure have tons of metrics that they use to evaluate it. But also plotting the data is super helpful because we can see there is a problem. The older people, their predictions tend to be a little older than they actually are. And the younger people tend to be a little younger. It's actually a pretty nasty confound to have because if you're studying something like anything that's correlated with age, you have a built-in confound. So you have to be careful. So there are methods now to help with that confound. And in this case, the correlation's high and the other metrics, the mean absolute error and the root mean squared error are all pretty low. So definitely plot it and just be careful. It's a huge pet peeve of mine when I'm reading a paper on machine learning and they're like, oh, we had great predictions. The correlation was 0.9. And then there are no pictures, no other metrics. So you really can't be sure. So this is just reiterating that perfect correlation doesn't imply good prediction. So here, basically, each actual value, the correlation is perfect, obviously, but if you look at the magnitude of the actual value and compare it to the predicted value, you can see that there's a really big mismatch there. So that's why I don't like only seeing a correlation without seeing the data. And cross-validation surely isn't a cure-all. So I teach a medical image analysis course here. And the final project is they have to process images of retinas to extract features from those retinas and then do a classification of a healthy retina versus an unhealthy retina. So I just give them, unfortunately, it's a small set of data, but a small set of labeled data. And I have a left out validation set that I use for grading. So I will never, ever knock points off because their left out validation was low, but I use it as a learning experience. And I would say most of the time, the students who have really high accuracies in their cross-validation end up with the lowest accuracies with the left-out validation set. And that's simply because they were developing their strategy for feature selection. And what they would do is they would extract the features in one way, run the cross-validation, and then extract them a different way, run the cross-validation again. So cross-validation isn't a cure-all. You need a left-out validation set. And if you're doing something like this feature development, you may even need 3 data sets, but again, you have to be careful. The first one is used to develop the features, and once you're done, you're done. You can't go back and keep doing it without running into the same overfitting problem again. Also, this is a big one. We're really used to compounds coming out in the wash, and I'll explain what I mean by that. So for this example, and I made this up, the paper didn't have tasks, but let's pretend there are 2 tasks, A and B. Let's pretend one of them's a math task and one of them's a reading task. And so the goal is to find areas in the brain that differentiate between math and reading. Well, obviously some people find math harder than other people. So there's this compound of difficulty that's built in. So what we're showing here are, this is not mine at all, but what they're showing here are 2 bold fMRI time series for 2 different subjects who do not show any math versus reading difference. The differences we're seeing here are actually due to difficulty. So let's say the first task is math, task A is math and B is reading. What we see here is that the subject 1 finds math more difficult than reading, and subject 2 finds reading more difficult than math. So in a standard analysis, if we were to estimate the mean task difference for each subject, we would get 4.75 for the first subject, negative 5.56 for the second subject, and then if we average those together, as we traditionally would in a multi-level analysis, we would not get a significant effect, which is great because these data do not have a task difference. It's only a difficulty difference. Now, if we instead do a within subject classification, we're going to get an accuracy that's 13 above chance for the first subject, 13 above chance for the second subject, and obviously if I combine those, I'm going to get a significant classification accuracy. So the problem here is that great classification accuracy might be incorrectly attributed to task classification, when in fact it is difficulty. So we have to think back when these tasks were originally designed, there are probably certain aspects of the task that we assumed would come out on average, just average out, that we don't have to worry about, like difficulty here. They're not going to come out in the wash if we're using a classifier type approach. So that said, don't be scared, dive in, ask questions, and be careful. And yeah, prepare to make mistakes. And that's how you learn. So let's see. I'm going through the questions again, and please ask more if you have them. Trading a test that cannot use the correlation coefficient. Yeah, so the correlation coefficient, the way I was talking about it was to assess the predicted values versus the actual value. So you would do the whole cross-validation so that you have predicted values for everybody and then correlate those. Okay, wait, maybe that's old. Can you estimate the expense associated with collecting fMRI from hundreds of individuals to ensure robust data analysis? Can I estimate the expense? I have no idea how much collecting fMRI data costs.
I guess you can talk maybe about the sort of cost-benefit analysis, right? If you're pressed to collect as little data as possible while still satisfying certain constraints of robustness, how do you think about that? How do you reason about that?
Wait, say that again?
When you can't collect infinite data, how do you reason about sort of how much data you need relative to the kinds of questions you'd like to answer? This is sort of a question about a little bit about sort of real life constraints and how you think about that when you try to reason about the experiments you do. I think Russ also addressed that in his talk a little bit by sort of saying, well, it depends a little bit on the cost of not finding the right answer, right? If you're like asking a question where the right answer, getting the right answer is very, very crucial in a sort of extra scientific sense, then, you know, then the cost is justifiable in some sense. But how do you sort of reason about how much data should you go and collect, given sort of what levels of robustness you'd like to get? Obviously, more data is almost always better, right?
Right. And I guess, I don't know if this is answering that question, but it's just something that came to mind. So I was working with some people, they wanted to study, they're studying traumatic brain injury in football players. And they wanted to collect fMRI data to see if that could somehow be used to predict how well, and again, it probably wasn't predictions, it was associations, but how well these people did after their brain injury. Well, the thing is, they already had a ton of measures that they could collect that worked really well. They had all these different tasks they would have people to do to test their like fine motor ability and other things. So it's, in that case, I feel like the fMRI data is probably a huge waste of money, and you should look at the stuff that's probably better, that you already know works, and see how predictive that is. But I don't.
I think that's fine. I think you can
Yeah, it's hard. Small
yeah.
studies are so unhelpful because.
Yeah, in some sense, yeah, you're wasting more money when you're doing a small study that can't answer any question than spending all the money to do a big study that can actually answer a question.
Yeah. Can parametric analysis of fMRI be done using machine learning? Not sure what you mean by parametric analysis. I think of, yeah, I don't know parametric in what sense, if you're talking about.
Maybe we can take that one on Slack, maybe ask that one again on Slack, and people will
give
different interpretations, and you can have more of a dialogue with the person who asked that.
It's a good idea. Are the coefficient signs interpretable in machine learning, or just the absolute value? It really depends on what you're using, and as I said, the whether your features are correlated or not, and the regularization that's used. That's the difference between R and R squared. You say you're using R, so you get highly correlated values that scale poorly, so R squared is bad. Is there a straightforward way to adjust the algorithm to make this work? Asking for a friend. Yeah, I'm not following that one either, so maybe, and plus we're getting near the hour mark. So
yeah, this definitely generated a lot of discussion here in the Q&A, and I'd really love to move some of this discussion into Slack, where we can continue this discussion after we log off from this. I will also post all these questions in like a weird CSV file into the Slack channel, but feel free to go over there and we can have more of a back and forth per Slack about all these things. And then maybe, yeah, we can end here. Thank you so much, Jeanette, for the talk and for engaging. That was great.
Yeah, thank you.